Oops. Hello, good morning, good day, good afternoon, good evening, good night, wherever you are in the world again. Let's have a drink. And welcome to another live stream here on Freaky Physics. And today we have a lesson, and there's CJ. Okay, so, all right, let me just let him in and we'll start. Hello, CJ.
Hi, Mr. Dennis.
How are you?
I'm good. How are you?
Doing good, thanks. Okay, retainers, what's that about?
Oh, my Invisalign.
Oh, I see. All right. Hold on. My board's still loading here. There we go. And we're gonna continue with the paper two we were doing last time, right?
Mm-hmm.
Okay, hold on. Let me just open that paper. Where is it? And here. Okay. Hold on. Give me a few moments. I am got so many windows open. I am confused which window I'm opening. Hold on, yeah.
Mm-hmm.
No, not that one. Is it this one? No, no, not this one. Not that one. It's mark scheme. There's also mark scheme. Hmm. I'll just open a new set. All right. So okay. Okay, I found the paper. So let's start then. I don't know what's happening. My internet's been really slow over the past few days. It's hard for me to load some stuff. Okay, so all right, so that's done there. Uh okay. And okay, finally it's loaded. All right, so let's continue with this. Huh, it's not loading. Huh, that's weird. There we go. Okay, so this is where we ended last time. We were doing the paddle and the ball, and this is the answer. Okay, right, so let's move on to the next question here. Okay, this is about circular motion. Okay, um, here.
All right, Mr. Dennis.
Yes, go ahead.
I got a free water bottle for completing the EE.
Uh-huh.
You too, right? I don't know. I don't know. They started giving out merch.
Say that again, sorry.
I got a free water bottle from completing the EE.
Ah, okay. Everybody does.
Yeah, it's really nice.
Mm-hmm. Right, so here, what was your EE about?
Like how Thailand avoided or evaded colonization.
Ah, okay. All right, so here's the first question for physics. today. Okay. First of all, explain why a centripetal force is needed for the planet to be in a circular orbit. Okay.
Um, this seems obvious, but I don't
Mm-hmm.
know.
Okay.
Um, wait. Because in order for a circuit to be in orbit, it would need to have a okay, um have a gravitational pull towards
Mm-hmm.
another
Okay.
object of greater.
All right. So there's a centripetal force. That's one mark. Okay. What's another possible mark here? Okay.
Um,
Mm-hmm.
Centripetal force keeps planets in circular orbit, but also allows them to not like get too close, like to stay in the same trajectory, like to stay
Mm-hmm.
in the same path without basically going closer and colliding with the
Uh,
source of the centripetal
that's
force.
still gonna be one mark because even
Oh,
though that's actually beyond what you're supposed to explain, it's not gonna get you a mark here. Okay. So the first thing you
okay.
said that there's a centripetal force is correct, right? And where must that force be directed at?
The center.
Center, right? Centripetal force directed towards center, right?
Mhm.
Towards uh center of the circle, center of orbit, right? There we
Mhm.
go. So that's the first part that would gain one mark. Okay, basically the idea here is you are looking into circular motion. So you have just to mention something special. There are a couple of things that you must always mention when you say when something's being described in a circular orbit. This is the first. The second one is um the velocity, okay, is perpendicular to the centripetal force. Or the
Mhm.
yeah, that just velocity perpendicular to centripetal force, right?
Mhm.
Okay. There are two other possible things we can state here. Okay. The third thing we can state here is that no centripetal force, right? No centripetal force means uh the planet will move in a straight line.
Mhm.
Okay. This is the third what okay. All right. And the fourth thing is kind of related to the second thing here. Okay. Second thing here. Magnitude of velocity doesn't change. Magnitude of v is constant, but direction changes.
Mhm.
Okay. Mentioning any of these four would gain you a mark. Now, in this case, you'll get a maximum of 2 marks. Okay. But direction changes. Okay. So again,
Uh,
mentioning any of these four will get a mark, maximum of 2 for this particular question. Okay, I'm looking at the mark scheme now, and yep, exactly the same thing.
wait, just to say magnitude of u?
V, magnitude of the
V. Oh,
velocity.
okay, sorry. Um,
Okay,
yeah.
magnitude of the velocity is constant, but its direction changes.
Mhm.
Okay. Um. All right. State the nature of the centripetal force. So, what is the force that's giving us the centripetal force? Remember, in orbit, there's only one force. When things are orbiting stuff, there's only one force that you really need to look at, right?
Mhm.
So what do you think it is?
The nature of the centrifugal force
Mm-hmm.
is oh gravity,
Correct. Gravity.
gravitational, or gravity.
Yeah. The safer answer would be to say gravitational force. Okay, that's a safer way to say it. Doesn't mean it's wrong to say gravity for now, but just in case you get an examiner who's gonna be strict with stuff. All
Mm.
right. On. Let's try this out. Okay. Uh. Okay, that's kind of working now. Uh. Just so you know, I'm trying to stream on Instagram.
Oh, really?
Yeah.
Oh, that's unusual.
Yeah, I found a plugin that would let me double stream into Instagram and into the rest of the other platforms.
Hmm.
Yeah,
Is your computer okay?
I got a new
It's a lot of
computer.
work.
Yeah, I just got a new computer and I just upgraded the RAM, so should be okay.
Hmm.
All right,
You
so
might have to change the CPU after a bit.
nah, hopefully not soon enough, I hope. All right, here's the next bit. So this time you're given data about the planet and okay, I'll just write the answer in a while. All right, so here's the question. Determine the gravitational field of the planet given this data. Okay.
Hmm. So I
They
used
go ahead. Which thing in the data booklet do you use?
6.222,
Mm-hmm.
the third equation.
Third
No, wait,
equation.
wait.
Correct. It is the third
Yeah, because
equation.
I am given mass and radius, and I have
Mm-hmm.
the g constant, gravitational
Yes.
constant.
Yes. Okay, so this is for your reference for now. And I'll just write the value of G, big G.
Mhm.
Okay. So the value of big G is, it's not given here, but it's in the data booklet. I might as well just say that. 6.63 times 10 to the negative 23 newtons meter squared per kilogram squared. Okay, that's the value of G. Go ahead and solve that.
5.83, but I do two sig figs, so it's 5.8 times 10 to the 5.
Okay,
Negative 5.
all right. This time I'm checking the mark scheme because I don't want to solve it. But yes, that's correct. You said, say that again. What's your answer?
5.8 times 10 to the negative 5.
Too small. It's too small.
Oh. Sorry, I forgot to square it again.
Yes.
6.4 times 10 to the negative 12.
Okay, so that's now correct. Okay, so if don't forget to do the squaring. A lot of people still forget. You still forget that quite a lot as well. Yeah, so I'll remind you right now. Yeah, so this is gonna be um small g is equal to big G mm over r squared. This is your g. Your mass is, sorry, no m, no big small m. Your big M is that, and your r is this. Put that in the calculator, you get this final answer. Okay. All right.
Wait, I
Let's.
get 6.63 times 10 to the negative 23.
Yes, that's correct for G.
Wait. Oh, okay.
Okay. So the final answer. Sorry, I forgot to mention that. So the final answer here would be, you were right, 6.4 newtons per kilogram. Okay.
Yeah, because
Oh,
the meter squared cancels out.
mm-hmm. You can also say this as meters per second squared. Okay.
Because it's
Meters per
acceleration.
second squared. Okay.
Mhm.
Okay. Next question. We're done with the circular motion problem. Now, this next question's about thermal physics. I think I'll copy this whole thing. Okay, and here we go. Okay. All right, so here we have the mass of 1 kilogram of water is brought to its boiling point of 100 degrees Celsius using an electric heater of power 1.6 kilowatts. So the molar mass of water is given. You have to estimate the average speed of the water in the water molecule, assuming it's an ideal gas. State one assumption of the kinetic model of an ideal gas and estimate the specific latent heat of vaporization of water. Okay, so let's do the first one, which is actually let's do a part two. State one assumption of the kinetic model of an ideal gas. Let's start with that. Start here.
Kinetic model of an ideal gas.
Mm-hmm.
Um,
There are 7 assumptions. You're not expected to memorize all of them, but you're expected to at least be familiar with at least 3 or 4 of them.
let me think. Mm, the distance between them, or can I say they all move a lot? Like
The
the
idea is
particles.
yes. The idea is correct, but you cannot say it the way you said it.
Okay, the
Okay.
velocity of the particles are equal to each other.
No, not quite.
Or can I say the distance between the particles are equally separated?
Mm,
Or
hmm.
do they collide a lot? Oh, the particles um collide a lot.
Okay. The best possible answer from what you said, from the things you said, is the last one. But again,
Mm,
if I'm being strict with the marking, that wouldn't get a mark. If I'm being strict.
okay.
Okay. Um. Okay. One way. Okay, I'll tell you the 7 assumptions. Okay, but some of those assumptions are actually like offshoots of the other main assumptions. Okay, so the first one is that you said it in a very similar way, but I would say it like how would I say this? The distance between the particles is large compared to the size of the atoms or particles. So that's what just happened. Oh, okay.
Wait, you said it's small compared to the size of the
So
atoms
again,
and
large.
particles?
Sorry, the other way. Large
Oh, large. Oh.
distances between atoms. I'm gonna use atoms now, okay? Are but the
Mhm.
best word to use here are particles. This particles are large compared to the atoms themselves. Okay,
Mhm.
so that's one assumption. Themselves. Okay, the second one, and this is the second one would be the interaction. The time of interaction between collisions is negligible. Time of interaction in collisions between molecules or atoms. Collisions between atoms is negligible. Okay,
Mhm.
that's one. That's two. The third one is related to the second one. If the time is negligible, then that means the force is also the attractive, actually, not even the force. The forces between particles are negligible.
Mhm.
Okay, so between atoms are negligible. Okay. The fourth one is an offshoot of the first one. The volume of molecules compared to gas. Okay. Compared to the gas is also negligible. Okay. Negligible. Okay. These four are enough. There are, like I said, there are seven, but these four would be enough to
Wait,
describe most
what force?
gases.
Why are the forces between atoms
Are
negligible?
Yes, they're negligible as well. Okay. So
But why?
that the reason for that is because um when we're talking ideal gases, there are, well, think about it this way. If this were an ideal gas, ideally, we don't want the particles to be interacting with each other except for during the collisions.
Mhm.
Okay. But in if this was not an ideal gas, then this would mean that there would be forces between atoms whatsoever, and those forces would tend to clump up your gas. So later on, there's going to be a chance that your gas is going to act like a liquid. Okay. So that's why
Mhm.
we need to say that the forces between atoms are negligible for ideal gases only. Real gases, you don't have to do that assumption for real gases.
Mhm.
Mm-hmm.
So what assumption would you make for real gases?
Uh-huh. For real
That the forces
gases,
between them are not negligible.
yeah. But yeah, you can say it that way. Or you can also say that, oh, actually that's the fastest thing that you can say. That's the easiest thing you can say. So the forces between atoms are not negligible in real gases. Okay.
Mhm.
All right. Okay. So let's take a look now at the first one, 1A. So we're given the molar mass of water, 18 grams per mole. Estimate the average speed of the water molecules in the vapor produced, assuming that the water behaves as an ideal gas, or water vapor. Okay. Okay, I'm gonna give you the the formula here. This is from 3.2.
Thank you.
Okay. Okay, so there it is. Which equation would be useful here?
The PV equals nRT.
Mm-hmm. Not quite.
Mm, really?
Mm-hmm. It could be, but there's a better formula to use.
Oops. Um, ah,
Actually, yeah, you can. We're looking for average speed, so we cannot actually use PV equals nRT here.
oh, that's volume.
Yeah, V here is volume, so yeah, you cannot use that.
The, where's R?
R is the ideal gas constant. Data booklet. R is, okay. I'll just write it here.
What do the capital N's mean?
Which N? This thing?
Like N and NA.
This thing?
Yeah.
Okay. So small n is number of moles.
Mm-hmm.
Okay. This big N is number of molecules or particles. Okay. Number of particles. And Na is Avogadro's number.
Mm-hmm.
Okay. Um, where are those necessary data? Okay. This is from the fundamental constants page. I'll paste it here just for values. So So there, Avogadro's number is here, and the ideal gas constant is here.
So that means I use the no. I don't need the second equation, right?
Not
Um, the last equation,
the last equation, but which form?
the first one.
Okay,
No,
KB there is given, Boltzmann constant. You could do that. You could. Right. Actually, yeah. There is another thing you can use. But I think I think the first one is going to be easier. Yeah.
mhm.
All right. But you're not given the energy, or you're not looking for
Cycle.
the energy, you're looking for the speed, right?
Mm-hmm.
Average speed.
None of them have speed in them.
Now, I'm going to give you something here, all right? You're correct to use this, right? So we're going to write that here straight away. EK equals 3 halves KBT, right?
And
Now,
on the other side, we do 1/2 mv squared, right?
correct. That's correct. So you're going to have to write here 1/2 mv squared equals 3 halves KBT.
Mm-hmm.
So from there, you isolate everything. You get V on one side, right? So
Yes.
you get V would be equal to square root of the 1/2 cancels out with the 3 halves. That's going to be KBT over M, then take the square root, right? Okay, the problem now is what is, well, you have KB, you have T, you're given the temperature. What's the mass that we're looking for?
18
But
grams.
that's 18 grams per mole, right?
So do you use the second equation?
Mm,
No.
no, you don't
Mm-hmm.
need it. You don't need it. However, I'm going to tell you this much. Remember that this is the molar mass, right?
Mm-hmm.
And this is also numerically equal, okay? Numerical, okay? Equal to the mass of one particle, one molecule, one atom, one whatever, okay? Again, the molar mass is numerically equal to the mass of one particle. But that's in atomic mass units, okay? All right, so how do we actually solve that? Uh, okay, that's grams per mole. We want that mass to be in kilograms per mole.
So
You have to
0.018.
0.018. So that's what you're, yes, exactly. So that's what you're going to put in here. Your KB is given. Let's look at the data booklet again. KB is 1.38 times 10 to the 23, right? So let's use red. 1.38 times 10 to the negative 23. Your temperature is 100 degrees Celsius, right?
Yeah.
But you need to do something about it. Okay, that temperature needs to be in
Um,
Kelvin.
Kelvins.
Yeah.
Yeah.
So that's going to be times 273, right? Oh,
Times
no,
2 is
300.
73.
373, right? Okay.
Mm-hmm.
Now, the molar mass, this is going to be 0.018. But remember, this is grams, right? Sorry, this is already in kilograms. But remember that Avogadro's number needs to be involved here as well. Okay. Why do we need Avogadro's number here? Hold on. Where's the 3? Okay. 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 Don't forget. I forgot the 3. There should be a 3 here, right? So there's a 3 here. Okay. Now,
Mm-hmm.
I'm gonna have to multiply this by Na as well. You're gonna have to do that. Okay, because that 18 grams per mole, that's 18 grams per a certain number of a certain number, which is Avogadro's number. But we're only looking for the um we're looking for the mass of one of the molecules. Okay.
Mm-hmm.
So okay, numerically equal to one. Let's go back here. So the molar mass is numerically equal to um one particle, but that is if you say it in atomic mass units. You still have to convert that to grams. Now, the fastest way to do this, okay, so the fastest way to do this is where can I write it? I'll write it off to the side here. Yeah.
So do I also multiply the 18 grams with
Hmm.
the answer I got
Yeah.
from the n, with the small n? 18 grams is small n.
Okay. So here's the idea. This is 18 grams per mole, and that's gonna be 18 grams per um Na number of particles, right?
Mm.
Okay. So that's gonna be 18 grams over 6.02 times 10 to the 23 particles, right? So this means this is gonna be whatever this number is, that's going to be the grams for one particle. Okay. And that's the mass we need to put into the formula. So whatever this
Mm.
number is, okay? So what if we just put that in the calculator? What would that give us? So that's gonna be let's convert that to kilograms. So 0.018 divided by 6.02 exponent 23 gives us 2.99 times 10 to the 20 minus 26 grams, kilograms already for one particle. Okay. So this mass is what we use here. So I'm going to have to erase this, and we're going to use that value right there from before. Okay. So once that's done, that's the answer. I think this particular question, even though it's 2 marks, this is a bit difficult because of the fact that you have to do a lot of conversions.
Yeah.
Okay. So what's that? That's 2.9910 to the minus 24.
There must be a shortcut because it is 2 marks.
There is no shortcut. I'm looking at the mark scheme. I just looked at the mark scheme, and yeah, it's the exact same thing. No shortcut.
Okay, just to confirm, you multiplied temperature with Avogadro's constant
I'm gonna remove that now just to make it clearer. Kilograms.
because you already did that with by converting the 18 grams.
Yeah, yeah.
Yeah.
So by converting the 18 grams into grams per particle, then yeah, that's what we get. Yeah. So we're
So we
removing.
multiplied that whole top part by 3.
Mm-hmm. So let's go
Oh.
back up, zoom back in. Yes. So this is the KB. This is the temperature in Kelvin. This is the 3, and this is the mass.
Mm.
Okay.
Wait.
Oh, sorry, that's not 24, that's 26. There.
Oh.
Okay, looking at the mark scheme. Okay, I'll tell you what the answer is from the mark scheme. It should be around 720 if once you calculate that.
Does this say 273?
That should be 373. Let me edit that. And then I use a lighter color, yellow, 373.
Wait, is Avogadro's number 6.02 times 10 to the 23?
Yes.
We got 516.
Mm-hmm.
Must have done something wrong.
Yeah.
Is it 1.38 times 10 to the negative 23?
Say that again, please.
The Stefan Boltzmann constant. What's the
1.38. 1.38
times 10
times
to
10 to
the...
the negative 23. It's right here.
Oh, okay.
Okay.
For me, it's kind of blurry. So, oh yeah, I still got 516.
Okay, I have an idea. I'll just rewrite the whole thing here. Hold on.
Oh, square root.
Yeah, and then the square root. Yeah.
Oh, then I got 22.7.
Oh, 22.7. That's too small. Okay. Let's redo that. Okay, so I'll just redo it from scratch here. So again, your V would be equal to, oh, let's make that smaller. V would be equal to, okay, so there. V would be equal to the square root of, can you read that? Oh, that's too small. Yeah, it's hard to read, isn't it? So hold on. Okay. Hmm. Okay, that didn't quite work. All right, I'll figure that out later. But okay, so okay. So where do you think you made the mistake while I'm doing this?
I don't know.
You don't know. All right, so let's go through it together again. So here we go. Okay, so again, uh, v squared will be equal to um 3 kbt all over m, right? So that would be equal to 3 times k given there as
1.38.
1.38 times 10 to the minus 23. So 1.38 times 10 to the negative 23. There's a negative. Let's put that there. 23. Then multiply that by the temperature, 100 degrees Celsius. So that's 373 Kelvin. And then divide this by the mass. So that's going to be 0.018 kilograms divided by Na, right? Or let's put
Oh,
that 6.02 times 10 to the 23.
I just put 2.99 times 10 to the negative 23 there.
Okay. That's if you actually substitute this in already, right? Okay, let me see if
Yeah.
this is correct. Real quick.
Oh, is
Let me
it to the
just,
negative 26?
yeah,
I
26.
got negative 23.
Okay, hold on. I think I may have
So,
miswrote that. Hold on.
oh
18
no, I misread
divided
it.
by 1,000. Okay, let's do that again. 18 divided by 1,000. That would be that.
I got 719.
0 to exponent 23. 2.99 e to 26. Correct. So this is correct, yeah? Now,
Mhm.
okay. So once
I
you've
think that was
done,
the mistake.
yeah, maybe that's a mistake. So let's find that
Now it's
velocity one.
719.
How much is it? 600 and
709, 719.
719. Okay, that's correct now. Okay.
Or 720.
All right. So once we put that in the calculator, let's do that again. Uh, that times 3 times 0.38 exponent negative 23 times 373 equals, then take the square root. Yeah, I got 718.6, which,
Mm-hmm.
okay. And of course, don't forget to round it off properly. Yeah. Round it off to the correct number of sig figs. In this case, what's the correct number of sig figs?
2.
2. So the final answer must be 720.
720.
Okay. So this would be 719 meters per second, which would be equal to 720 meters per second to sig figs. Okay. So don't forget the sig figs. Right. I think we got that now, so we're okay. Yeah. So let's go to the next bit. Um. Okay. So you have a mass of 0.86 kilograms of water remaining after it's been boiling for 200 seconds. So estimate the specific latent heat of vaporization of water and state an appropriate unit for your answer. And then second one is explain why the temperature of the water remains at 100 degrees at this time. So specific latent heat of vaporization. All right, let's take a look at some given info again. I think we need to go back here. So we have this power given. We have this power given. You're also given the mass, initial mass, right?
Mm-hmm.
Mm-hmm. So, and last thing, of course, data booklet formula. First one,
Q equals L.
ml, correct. Q equals ml.
So Q is the energy. So
Mm-hmm.
find the work overtime
Right.
or power overtime.
Power over time, not power over time. It's power
Just work.
times time.
Oh, energy overtime or
Yeah.
no wait.
Remember,
No,
energy
Q is
is,
energy, right?
yeah, Q is energy.
Yeah, okay.
So to find energy, you're given the power, multiply by time, right?
Mm-hmm.
Okay.
Power is 0. No.
1.6 kilowatts.
Yeah, wait. Oh yeah, 1,600
Mm-hmm.
times 200.
Okay, so 1,600 times 200, correct, equals,
That's cute. That's 3,000, 32,000.
that's 32, two zeros, right? Four zeros,
320,000. 320.
320,000, correct. So that's the Q side.
And
How about the ML side?
divided by, oh, sorry,
Okay, yeah. So you're
divided by
dividing
zero
this
point eight
by
six.
0.86 is not the correct number to use.
Um, hmm,
Okay, remember it says here it's remaining. The mass of 0.86 is the mass remaining.
mhm.
In latent heat, you want the mass of the bit that changed
So,
state, right?
mhm.
Because that's the idea. Latent heat is always about changing state. So we're not interested in the 0.86. We're interested in the lost
Zero point
ones.
zero one eight. Oh,
How much mass? How
what's the
much water
last
do you
one?
store?
Oh, 1 kg. So
1 kg.
1 minus 0.86. So
Mm-hmm.
0.14 change.
So this is gonna be 0.14 here. Okay.
Mhm.
So,
So I got 2.29 times 10 to the negative 6.
2.29 10 to the negative 6. No. You got the
Oh, positive 6, positive 6,
positive
my bad.
6. There we go. So 2.29. But again, sig fig. So this should be 2.3. Okay. Times
Mhm.
10 to the 6 joules per kilogram. Okay. Oh, by the way, yeah. In this case, you're supposed to state the unit. So, yeah, just make sure you mention joules per kilogram here.
Mhm.
Okay. All right. Explain why this temperature of remains at 100 degrees during this whole process. Why does the water temperature remain at 100 degrees?
Um, because as it's going through a phase change, the
Mm-hmm.
energy's the one that is okay. Not the energy is the one. The instead of temperature changing, the energy has to be put in order to change the temperature after the phase change.
No, not the answer.
What's the one more?
Okay, I'll give you a clue. Remember, this is liquid to gas. Remember what I said earlier? If it were not an ideal gas, we can sometimes consider it to be a liquid, right?
Mhm.
So, what's so special about liquids compared to gases when it comes to their molecules?
They
L- Let's go back
stick
to
together.
yeah, they stick to each other exactly, right? So if they stick to each other, then there are gonna be forces between the molecules, and therefore they're not negligible at that time, right? So what does that
Mm.
energy do? What does that energy
The
do?
energy separates the molecules.
Mm-hmm.
It separates the molecules. Oh,
Okay.
energy is used to separate the molecules.
Set.
Therefore, the temperature remains the same.
Okay.
Plus, it's boiling point. It's the boiling point.
Okay. Hold on.
Can I just say 100 degrees is the boiling point of water?
Yeah, but you don't have to mention that exactly. The thing is, it's already correct. Just saying the energy, this is what you said, right? Oh, I'll make it a bit bigger. So the energy used to break the to what did you say again? To break the bonds, right?
Mhm.
Between water molecules. This is already one mark. That's the answer. The idea here is latent heat is latent, so to speak. It doesn't change the temperature because it breaks the bonds between the atoms, and therefore it changes its state in the process.
Mhm.
Okay, all right. So that's one mark. Let's go on. Okay, is that clear now?
Yeah.
All right, we're not done yet with with heat. We still have a couple of questions. Okay, first question here is this. Okay, so you have the heater, it's removed, and a mass of 0.3 kilograms of pasta at negative 10 degrees is added to the boiling water. Determine the equilibrium temperature of the pasta and the water after the pasta is added. Other heat transfers are negligible. In other words, the heat transfers strictly between the water and the pasta. Okay.
Mhm.
Okay, so how would you solve this? I would I'm gonna give you something to help you out. Okay, so you try to remember that you wanna make sure that when they're done, when you're done doing this particular thing, the temperatures are equal between the pasta and the water. So when
Water.
you're mixing something, the final temperatures must be the same. Okay.
Mhm.
All right. So
Oh, so can I do can I put MC delta T on both sides or no?
yes, yes, you can.
Okay, but one being -10, the other being 100 degrees.
Uh-huh.
Or zero. Is it zero? Because the
No,
never mind.
no. Okay. So you're right. You're gonna have to do MC delta T on this. MC delta T. Right? I'll just write here pasta and then water, right?
Mhm.
Okay, so let's put pasta, 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 water, 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 right?
Mhm.
Okay. Now what?
Water is 1 kg, right?
No, remember, no,
Oh,
you don't have 1 kg anymore because you still have the same problem where the heater is now removed, right? So you
so it's
don't use
still the leftover water.
the leftover water. So let's go back here. It was
0.8
0.86, 0.86 here, 0.86 kilograms.
times
This, uh-huh,
4,200
joules per kilogram
joules
per Kelvin, correct?
um,
What's that? What's that?
times 100.
It's not 100.
Yeah.
Now, the idea here is you have your pasta, you have your water, right? That leaves you the pasta in the water, right? So this started off as
Hmm.
-10, and then this starts off at 100, and then this starts off at a temperature T, right?
Hmm.
So with that, how do you find your change in temperatures?
I think this is the tea because it's not being boiled.
Mm-hmm.
The heat is removed.
Mm-hmm.
So
So
this is just tea.
no, not T. This is 100 minus T.
Hmm.
Okay. All
Oh,
right.
yeah, yeah.
Also, one more thing. I'm gonna put a negative here. Also a negative here. Okay.
Hmm.
Why does this exist? Because remember, the water loses energy, right? Or loses heat. That's why it's negative. The pasta gains heat. That's why this is a positive. Okay. So with that, let's continue with doing it on the left side, the pasta.
Hmm.
So the mass of the pasta
It's
is in
zero
this
point two 3
0.30. Okay. C is
times 1,800.
okay. Joules per kilogram per Kelvin. And then what's your change in the temperature?
Oh. Oh, -10 plus T.
No.
No? Oh, -10 minus T.
It's gonna be T. Oh, hold on. I think I better change this. Okay. This should be T minus 100 because remember you're going final minus initial, right?
Mhm.
So this would be the same. You're doing final minus initial. So your final
T mi
temperature is T, right? Then minus your initial temperature is -10.
minus neg
So minus
T
neg.
plus 10.
So this becomes T plus 10. Yeah.
Oh,
So you were right to say T plus 10
I
earlier.
said -10 plus
Ay,
T,
-10 plus T. No.
so it's different.
So it's different. Yeah.
Yeah.
All right. So there we go. Let's now solve for T.
Mhm.
Okay. In this case, it's going to be way easier to do all the math with the numbers first, right? So
Mhm.
do all the math first with the numbers. Usually it's easier to do the algebra before the arithmetic. In this case, arithmetic's going to make it easier. So where's my calculator? 3 times 1,800. This is going to give you 540 times t plus 10, right? On the left side. And then on the right side, you have 4,200 times 0.86. So this is 3,612 times t minus 100. Then we have a negative, right? So finally, not yet actually, we distribute. That's gonna be 540t plus 5,400 is equal to negative 3,612t plus 3,612, two zeros. So finally, let's move stuff around. So when we move stuff around, we get 540t plus 3,612t is equal to 361,200 minus 5,400. And then from here, factor out the t. And then let's add that 540 plus 3,612. That's going to be 4,152. That's going to be on the right side, 361, 200 minus 5,400. Again, 361,200 minus 5,400, 355,800. And then finally, t is this number divided by 4,152. Final answer is this, 85.69 degrees Celsius, and that's going to be 86 degrees Celsius, two significant figures. Okay.
That's interesting. I got 85.98, but it still rounds off the same.
To 86. Hold on. Maybe we have slightly different values. Not so sure.
I just did the numeric solver thing where
okay.
I just put in the equations at face value.
Right. Okay. Sure. But either way, it's going to give you 86.
Yeah.
Okay, so
Yeah.
we're good, yeah?
Mhm.
86. Okay, 86 degrees Celsius. Right. So next question here. Where are we? Okay, so this is 3 marks, so definitely worth the 3 marks with all this solving, right? Okay, so let's move on. Next question here is gonna be about the electrical heater itself. Okay, so in other words, since this is about the electric heater, this is gonna be about electricity. Done. Okay, I just want to say, okay. Just move it here, increase the size of it. Okay, so the electric heater has two identical resistors connected in parallel as so. And then the circuit transfers 1.6 kilowatts when switch A only is closed. The external voltage is 220 volts. So which one would be? Okay, so show that each resistor has a resistance of about 30 ohms. So you're going to have to use one of these formulas here. Okay.
The one with power in it.
So which formula would be the best? Sorry, say that again.
I said the one with power. So
Yeah.
P equals V.
You're given
no,
V.
P equals V squared over R.
V squared over R is correct. So find R, right?
Yes. So V squared over P.
So R is equal to V squared over P. And that's going to be, our V is 220 volts. And the power is given as 1.6 kilowatts. So 1,600. All right, let's take a look. What's the actual value then?
30.
Okay, 220
0.25.
times 220. Yep, divided by 1,600 is going to be 30.25. So there, shown. Again, show, you have to do this. The two things, okay? You give an answer to a more accurate value. 30 ohms, like that. Okay.
Mhm.
Next, okay, and this is the last question for this bit. So calculate the power transferred by the heater when both switches are on. It's 2 marks. Uh, okay, there's a logical way to do this, but since it's calculate, you really have to show by calculation. Okay, so how would you do this?
When they're closed,
So when switch B is
then
closed, what happens?
the if it's closed, then there's no wait. If the heater is off, it's not heating. Therefore, like
Mhm.
when it's
Remember, when we
closed,
say closed, remember when we say closed for circuits, as switches are
does it mean
closed,
it's
that
open?
means you turn it on. I-
Okay.
It's
Oh,
not.
it's in parallel.
Uh-huh. So they're in parallel, correct?
Hmm.
So the resistors are
So
in parallel. So what's the overall resistance?
um, overall resistance. So it's one.
Mm-hmm.
Okay, 1/30 plus 1/30.
What's that equal to?
I mean, equals to 2/30, which you have to flip, so it's 15.
So you're right. So in this case, RT is equal to 15, correct? 15 ohms, right? So with that, what
Mm-hmm.
do? You now find the new power.
Mm-hmm.
So
So
that's,
V squared over R.
yes. So power equals V squared over R. It's going to be 220 squared over 15. So what's that going to
Wow.
give you?
3227.
Okay.
Oh, watts.
Okay.
3.2 kilowatts.
3,200 watts or 3.2 kilowatts. Okay. That's how you calculate it. Logically, I'll say another possible solution. Okay. But logically,
Mm-hmm.
but you can't use it in this particular case because it says the term is calculate, right? Okay. But logically speaking, think about it this way. Go back to the circuit first. So remember um, in parallel, the current through A doesn't change. Whatever that current is, it's still current through that, right? But when you close B, that means it's drawing its own. So let so let's put a value for it. For example, this is drawing a current I. When this is closed, that means that current here is I, right? At the current situation. But now, when you close that, this is going to also draw I. So this means this is now 2I. So twice the current, same voltage, twice the power. Okay. Or another way to do it logically is since they're in parallel, each one takes 1,600 watts. So there are two of them, total of 3,200 watts. 200 watts. Okay.
Mhm.
Right. So that's the last question there. Let's go to number 4. Oh, okay. A little bit of astrophysics, but remember, this is not really astrophysics. This is topic 8. Okay, so in this case, let me read the question real quick. So a planet orbits at a distance d from a star. The power emitted by the star is P. The total surface area of the planet is A. The first one is explain why the power incident on the planet is only 1/4 of that area. Okay. Basically, why is there that 1/4? And then the second question is about the albedo. So I'll just put this here. So what's your answer here for A part 1?
Hmm. What is the incident on? What's the incident? What's the power
Incident.
incident? Like, is that?
Uh, okay. Remember that the power emitted by the star is P. So how
Mhm.
much of that power goes into the planet? So that's what's asked. So basically, that's the question here.
Hmm.
How much of this power? How much power is on the planet? Oops.
Um. Hmm. Big. So that's the distance squared. Oh, is this on the formula booklet? I think
Not quite, but let me double check. But I don't think it's exactly in there. Uh,
it's similar.
it's similar, yes. I'll just paste the formulas here. All right, I think you need help on this one. Okay, so I'll guide you through it. I'm not
Ah.
telling you step. Let's do it step by step. Yeah. So first of all, try to draw this first. Draw the star and the planet. Basically, draw this
Mhm.
particular bit here. The description. Okay.
Mhm.
So draw this description. So your planet's a distance d from the star. The surface area of the planet is A. The power emitted by the star is P.
Mhm.
Okay, so how would you draw this?
This the star and the planet.
Just a star in the planet. You just say that's D, right?
Yeah.
Okay. And then this emits P all over the place, right?
Yeah.
Now, the idea here is that that star emits that power in a sphere around itself, right? So P from
Mhm.
star uh, radiates in a sphere.
Yeah.
Okay. So
Isn't that
this
the? I was thinking, isn't that the luminosity
it is. It
equation?
is. It
Yeah.
should be.
Or the brightness.
Uh okay, if we do this in terms of astrophysics, power is luminosity, okay? Luminosity. And then brightness is intensity.
Mm.
Or let's do it the other way. Intensity is brightness. Okay? So
Mhm.
that's that and it's that. Right. So so this is the first part. The star radiates all its energy in a sphere, right?
Mhm.
Okay. And then if we zoom in into the planet only gets its radiation on one side, right?
Mhm.
So what happens to half of the earth, half of the planet? It doesn't
It
absorb
doesn't get
anything.
it.
So
Mhm.
that already cuts it in half, right?
Yeah.
Okay. The third part, and this is the one that's not so obvious, is
Power
okay.
over area.
Okay. Is this okay? It's not very well explained in IB for some reason. You don't need to explain it this way, but I like explaining it this way. Okay. The
Oh,
idea here is this section of the this section of the planet is curved. It's not a flat surface, right? So basically
yeah.
at this point, you're getting max intensity, right? I think I better do it some other elsewhere. I'll do it here. Okay. So again, if we're doing only half the planet like that, and then let's do all that light rays here, like so. Okay. So this thing, okay. So let's take a look at where that lands. Okay. So these rays land here, right?
Mhm.
And then if I pick two more rays that are like these guys, and I'm gonna do that, it doesn't land on a similar area. It lands on a bigger area, right? Now, if I do the same thing here and I put another one here, and let's use, I don't know, let's use green on this one, there and there, right? You see that the higher up you go on the surface or the latitude, so higher goes, the higher, oh, the further north you go or south, right? From equator, intensity decreases, right? Okay. The effect of this is this decreasing intensity across the surface of the planet. This makes the average intensity across the planet, okay, half of initial half of light intensity, half of maximum, okay, light intensity. That's the reason why. Now, that's the way I explain it because it makes a whole lot more sense, right?
Mhm.
Okay, but IB is okay with you saying that um, this has the effect of cutting the area in half. Area by in half, not by, in half. Okay, so you
Mhm.
do basically it's the same thing. So only half the planet is exposed, and then and then of that half that exposed, it's essentially got an effective area of half of the actual area because of this thing. Okay. So that's the idea. How would I write it in as an answer? Okay. How would I write that as an answer here? Where can I write it? I think I'll write it here on the side. Okay. So I'll just write it here. Answer. Okay. Um, area, uh, one half area is in darkness, right? Darkness and does not absorb radiation.
Mhm.
Okay. So so this now means we are now the intensity now is equal to the power over one half area already, right? Okay. Let me see what the question is again exactly. Explain why the power incident is that. Okay. Um. So from here, that's already um power equals one half IA, right? Okay.
Mhm.
So incident. Okay. Incident. Okay. Now the second half is um planet curvature planet's curvature makes IA average equal to 1/2 I, right?
Mhm.
Okay, so that means the total average power now would be equal to, sorry, not like that. So the power incident now will be equal to 1/2 of 1/2 I max, right? Over A times A. And now we're gonna put in the things for the intensity. So that's gonna be 1/4, and that's gonna be I max would be equal to P over area. What's this? 4 pi d squared times A. Okay, where this where did I write like that? So weird. 4 pi, not pi 4. 4 pi d squared, and this 4 pi d squared is the area around the sun, around star. And there you've just shown it. Okay.
Wait, but wait. So when it says explain, I have to use these numbers.
Yeah, you have to explain the numbers.
I can't say it's 1/2. Or it's not 1/2. It's 1/4.
It's gonna be 1/4. Yes.
Wow.
Yeah, I know. It's
Okay.
so once that's done, you just have
And
to remember it. Okay. Most of the time, you just have to remember this fact. This is the first time me seeing that you have to prove it. But most of the time, you just memorize this fact. Okay.
the fact that it
Yeah.
is 1/4 an area of is around a star.
Yeah. So a planet going around the star will have an effective area of 1/4 its actual area when absorbing
Is where
radiation.
it's lit up.
Hmm.
So 1/4 its actual area is lit up when a star is going around it.
Yeah.
Okay.
Okay. All right. Okay, let's take a look at the second part. Albedo is given with alpha P. The equilibrium surface temperature of the planet is T. Derive this equation where emissivity E of the planet is known. Oh, okay. I think once you see something on the formula, you know which part of the data booklet you need to look at.
Hmm.
Okay, I'll help you out
Uh,
by posting the formulas. You can just check. You can just use one formula there anyway.
the hmm,
There.
what's up with the alpha?
Uh-huh. It's got albedo, right?
Yeah, it's
Mm-hmm.
the first equation.
Yeah, okay, you're gonna have to use the first equation, definitely. But you're gonna have to use another equation.
The last one.
The last one because of albedo. Correct. So what are you gonna do? It says equilibrium, right? So that means power in equals power out. This is where you
Mhm.
start. So what's a power in? This is where you use power
Uh,
in. Okay, and this is your power out. Okay.
oh,
Al-
so on one side I use albedo equals no.
yeah, yeah.
Never mind.
So yeah, that's
Really?
correct. Yeah, it is. It is. Okay. I think you will also need the date. Actually, no, you don't need the data. You need to prove that that's a formula, right? So just remember that the power emitted by the star is P. So let's put that up here.
Mhm.
Okay. Power emitted by the star is P.
Wait, can I do 1 minus total scattered
Mm-hmm.
over total incident? Power 1 minus total scattered over total incident? Or no?
You could, but that's not. Yeah, you could actually. Power. Uh, star equals P. Keep that in mind. All right.
Mhm.
You could do that. Actually, you need to do that somehow. Okay, remember power in is the amount that goes into the planet. But albedo is the part that
That's
gets
reflected.
reflected. So you're right. So that's why power in is equal to what? Power
Um,
minus
oh, minus albedo.
uh, albedo, power times the albedo, right?
Mhm.
Okay, which is equal to power times 1 minus alpha p. That's your power in. How about your power? How about your output power?
I'll put albedo. Wait, power plus albedo.
No. Remember, this is your formula for
Yeah,
out, right? So that's emissivity.
emissivity.
So emissivity, we don't really know what it is, and we says we're not going to ignore that. Sigma is a constant, right?
Mhm.
What's the area of the planet that emits it, not absorbs? Yeah. What's the area of the planet that emits things?
The area of the planet that emits things. The
That
surface.
emits the heat. So the total surface, or is it like just part of the surface?
I mean, emits it as a sphere. A sphere.
Yeah. So the whole thing, right? So
So
that's
the whole.
gonna
Yeah.
be area, correct? And then t to the 4, right?
Mhm.
Okay. So what do we do now? What do we do now? Power in equals power out. So what we do?
Oh, we put p minus power of the albedo.
So this thing,
Oh, power times up. Yeah, p minus p that
uh huh,
equals e
equals.
Stefan a t to the fourth.
And since we're looking for temperature, move everything, right?
Mm-hmm.
Mm-hmm.
So it's the same equation.
Uh huh. So t to the 4 will be equal to power times 1 minus alpha p divided by emissivity sigma area. There, right? The problem now is, what's the area? This is a sphere. There's a sphere, right?
Mm-hmm.
Uh huh.
Oh, can I just say pi r squared?
No, because remember, this is still a sphere, not pi r squared. There should be a 4.
Oh, 4
Okay.
pi r.
Yeah, so in this case, I'll just do 2t now, right? That's going to be fourth power, or fourth root. So we have power 1 minus alpha p over um 4 pi r squared e sigma, right? But if we look at the formula, there's something missing. We have 4, but the formula says 16. We got everything else in there, right?
Mm-hmm.
R is going to be emissivity. Hold on, let me double check something. There's something wrong here because we need 16, but we got 4, right? Is there
That
anything
must mean the
else?
radius is 4,
Aha.
or the one of those values, either radius or the emissivity is 4.
Mm-hmm. Mm-hmm. So one of these values should give us a 4 somewhere, right? Okay, so let's take a look from the beginning. What went wrong? Okay, so first of all, this is correct. The power out is definitely correct. Okay, so this is definitely correct. Um, this power incident onto um the power incident onto the planet is gonna be equal to just, remember, we need to divide this by 4. We need to divide that by 4. Okay. Why do we need to
Why?
divide that by 4? Hold on. It's going back to this. Going back to this. The power incident on the planet is
Oh,
already this.
yeah.
Okay. So we're gonna have to use that fact there. So um okay. Okay, so what else are we missing? Power equals area times over 4 times okay. I think I better just erase this bit to make it easier. Okay. So remember, um so the power in, I'll write it this way. Power in will be equal to 1 minus alpha p. So that's correct. And then the power incident is the one given here. P times 4 pi d squared times a over 4. Okay. P a over, what's the formula again? 4, that's going to be 16 pi d squared, right? 16 pi d squared. Okay. Now we're going to put that in here. What are we going to need to erase this bit? A power in this thing, right? Okay, so we're left with 1 times 1 minus alpha p times pa over 16 pi d squared. So what happens? Area cancels out, right? And from there, we get it done here. So let's just erase everything, and done. Okay. So t to the 4 would be uh 1
Oh, it's
minus
pi d squared.
mhm,
Okay.
1 minus alpha times p all over 16 pi d squared e sigma, and therefore done. We take the fourth root, it's the same thing. P times 1 minus alpha times 16. We can just rewrite it the way it is in the formula. Okay, 16 pi d squared e sigma.
Mhm.
Done.
Mm,
All right. So let's move on to the
wait,
next
wait,
bit.
wait. I'm
Okay, I think
still.
you're still processing. Go ahead. Which bit still confuses you?
Uh, I understand that you. Actually, no. You cut the A out on the other side on top,
Yeah, this A and this A,
but
right?
then yeah.
Mm-hmm. Because remember that A is the area of the planet.
Mhm.
This D is the distance from the star to the planet.
Distance. Uh-huh.
Okay. All right. Anything else?
So we don't need the fourth equation. The albedo equals total scattered and total incident.
We don't. We don't actually need it, but we need its idea, which is this is scattered, right? We don't need the formula itself, but we need the idea
Oh,
that this is
the in and
scattered.
out.
Yeah. So the absorbed would be the remainder, right?
Mhm.
Okay.
So we don't need the 4 pi r squared because we could just cancel the areas out because both
Yeah.
sides
Yeah.
had area.
Yep.
Okay, that makes sense then.
Okay. All right. So let's take a look at the question, last question on this section. So on average, the moon is the same distance from the sun as the earth. Okay. Basically, this question is about you just calculate the temperature, surface temperature of the moon. Now, here's the thing, you don't have to overthink this. You're already given a formula in the previous section, right? So use this formula basically to solve for the surface temperature of the moon. I'll give you one thing though. What is The solar constant, I'll just define this, okay? Okay, in case you don't remember, the solar constant is the intensity of the sun's radiation where we are. This is equal to intensity of solar radiation um, are at um, Earth's orbit.
Mhm.
Okay. There is a slightly different way of saying it, but I like saying it this way because it kind of makes it clearer in my opinion. So anyway, going back here. So the emissivity is given, albedo is given, solar constant or intensity is given. Find the surface temperature of the moon.
So we use the same
Mm-hmm.
equation.
Mm-hmm. Yes, you do. But the problem is you're given intensity and not power, right?
Hmm.
Okay.
But you said earlier power was no intensity was brightness,
Yeah.
and power was luminosity.
Uh-huh.
So if so, we're not given luminosity. Huh.
Mm-hmm. Uh emissivity is one. T Oh sorry, that looks like T, doesn't it? That should be pi.
Mm, where's B? Where's B? Can I put P as intensity instead?
No, no, you really have to use the definition. Power is intensity times area. Okay.
Mhm.
This is where I think this is the thing you need to do.
Oh, yeah.
Okay.
Is that in the booklet?
It is in the booklet.
Oh, yeah, yeah, I see it. I see it. Okay. Um,
Now, here's the thing. What area are you going to use? Again, we keep saying the same thing over and over again earlier.
the surface, the moon's area,
The
which
moon's
is
area, correct. Okay, I think, let me just check.
what's the radius?
Fourth. Okay, that's a question. What's the radius, right?
Is it? I'm just gonna say 4 because earlier we were wondering
Mm-hmm.
why it was 16 and it was 4, and the only
Uh-huh.
number you could have changed earlier was the R
Uh-huh.
because E has to be 1 or less,
Uh-huh.
and um, Stefan Boltzmann is a constant.
Uh-huh.
Is it wrong? Am I saying something wrong?
No, actually no. But there's something that you're not realizing at this point. What's that area that we
Yeah.
need? We're not. Yeah, it's true that we need this to be the area of the moon, right?
Mhm.
Okay, but okay. So hold on. Let me just try to say it in a more digestible manner. Hold on, yeah. Give me like a minute to think about how to say it. So you're given the solar constant, and you need to find the power from that. Okay, so basically go back here. This is the intensity. Now we can think of this solar constant again. So remember our drawing again. So this time I'm gonna use the sun and the moon here, right? So again, you're looking at, remember that the intensity here is the solar constant. But that's gonna be equal to this has a power output P, right? And this has a distance D. So our intensity here, right? So our intensity can be thought of to be equal to the power over the that area of that sphere, that's gonna be 4 pi d squared. Okay, so that's your intensity. So from here, what can you say what the power is? Power is simply intensity times 4 pi d squared, right?
Mm-hmm.
Okay, now put
Oh,
this in here.
we don't know D.
So what happens? 4 pi d squared cancels with 16 pi d squared, right?
So therefore it's 4 E Stefan.
Mm-hmm. So from here, temperature would be equal to the fourth root of power times 1 minus alpha p all over 16 and 4 cancel out, leaving you 4. Pi d squared cancels out. You're left with E sigma. Done.
Hmm.
So once that's done, put your values in and calculate.
But we don't know P, right?
We do. Sorry. This is now intensity, right? Because we
Oh,
substituted power. Sorry, my mistake there.
oh, right, right.
That's now the intensity, not the power anymore.
Intensity was power over area. Or is it intensity equals? Wait.
So let's try to highlight that.
Mhm. But if you did substitute it, wouldn't area be on the numerator? But then,
No, because this. Oh, yes, it would be. But remember, this area here that we want is not the area of the moon. It's not the A in the problem. The area that we want here is the area of that sphere around the sun.
mhm.
That's why I wrote it as 4 pi d squared instead of saying area, instead of saying A. Okay.
Mhm. Mhm. Wait, so it's not I times 4 pi d squared. It's
Yeah.
I divided by 4 pi d squared.
No, it's I times. Sorry. It doesn't look clear there, doesn't it? I'll just rewrite. Yeah, because you're getting it from this.
Mhm.
Because you're getting it from here, right? So if you rewrite that, that's gonna give you power is equal to, I'll just write it like this, 4 pi d squared I. Substitute in
Yes.
form, yeah. Then substitute that in the formula um, in part A2. Okay.
But then it turns into 4 pi d squared I 1 minus dp
Mm-hmm.
over. Oh, never mind. Yeah, you're right. I think I
Mm-hmm.
see it now.
All right. Okay.
Yeah.
I think, yeah, I'll just make it this a bit more clear. So in this case, we're still going to use that formula from earlier. Temperature is equal to the fourth root of power 1 minus alpha A, alpha P over 16 pi d squared E sigma, right?
Mhm.
So fourth root. So we substitute power in, so that becomes fourth root of power is 4 pi d squared I times 1 minus alpha p all over 16 pi d squared E sigma. 4 pi d squared cancels out, that becomes 4. Then substitute when done. Okay.
Okay.
All right.
I got 278 Kelvin.
Kelvins. Yes, this should be in kelvins.
Yes, because it's cold
All
and
right.
there's not
So in
much
this
atmosphere.
this gonna give you 270 Kelvin, 2 sig figs.
Oh, yeah,
Okay.
280.
Ah,
Shoot.
you're a bit too high. I wonder why. Because the marking scheme answers 268 Kelvin.
What was the
Stefan Boltzmann constant is 5
no the top one? I did 1 minus 0.87
0. No, it should be 0.13. So
for the
if,
top,
yeah, so hold
but
on.
that's albedo.
Yeah. So remember, absorbed, right? It's still about the absorbed thing. So that's gonna be 4 times intensity was, what was it? The given value? 1.36 10 to the 3. 1.36 10 to the 3. This is 1.36 times 10 cubed. This is gonna be 1 minus the albedo of
Uh,
0.13. Okay.
mhm.
And then finally, the last part would be 4 E sigma. So, of course, these are just values. You just plug them into the values later.
Now I got 450.
Okay, let me double check that.
Because the
Calculator.
E was 0.13 times
Mm-hmm.
5.67 times 10 to the negative 8.
Okay. Times 0.87, right? Then divided by 4 times E is 1. No, emissivity was 1, right? So sigma
Mhm.
is 5.67 exponent negative 8, okay?
Mhm.
All right, and then take the square root. Take the square root again. Yeah, I get 268 or
Wait, what
269.
was the E again?
E is 5.67. I'll just write it here.
E is 5.67.
5.67 times 10 to the minus 8.
Isn't that the sigma?
Sorry, that's you're correct. That's a sigma. The emissivity in the problem was 1.
Oh, the what was 0.13?
That's the albedo.
Oh, I saw that wrong then. Then I got 270. Yeah.
Okay. All right then. So, okay. Okay, let's take a look. Okay, so that's the end of that question. I think we have time to do this radioactivity question here.
Mhm.
Okay, radioactivity. Okay, so okay, so here's the question. So you have radioactive uranium-238 produces a series of decays ending with a stable nuclide of lead. The nuclides in this series will decay by either alpha or beta minus processes. So only beta minus. So first question, uranium-238 decays to a nuclide of thorium-234. So write down the complete equation of this radioactive decay.
It's alpha decay because okay, so it's 234
Mm-hmm.
TH
Correct.
90
234.90.
234
Okay.
plus
Plus.
um 42HE.
Okay, you can either say alpha or you can say 42HE. Both of these would be correct.
Oh, okay.
Okay.
Hmm.
I personally
Wait,
prefer
could
this, but this is also okay. Yeah.
hmm. Okay, can I just put alpha instead of the 42? Because isn't alpha always 42?
Yeah, alpha is always 42 anyway. So yeah. But you have to write
So
either
I could
alpha
just
or helium. Okay.
okay. But I don't need the 42 for the alpha part.
Uh it would be safer to write it. To write the 42. Just safer.
Okay.
Okay. All right, next question. B. So we have thallium 206 decays into lead 206. Identify the quark changes.
Hmm. Quick changes?
Mm-hmm.
Well, they add another proton
So
or no
okay,
neutron.
what did you lose or add a proton?
Wait, was that?
Did you
Wait,
add or lose a proton?
you add one.
So proton
Wait,
added, right?
wait.
Proton added. So that means what happened to the neutron?
Wait, is the atomic number? Um,
This is 81. This is 82. Let's zoom in a bit so you can
that
see.
means 82 protons, right?
Yeah, 82 protons.
Okay. So that means uh the quark. Okay. That's like a up down down isn't a quark, right?
Mm-hmm. So, correct. This is
Oh,
up.
it is up down down.
So you
Oh,
start
up
with up,
down.
down, down into what?
Up down.
Up, up, down. Okay. This is, oh, sorry, up, up, down. Like that. Okay, but this is already correct. But you could have said also a down quark changes to an up quark.
Hmm.
So this would also be correct. Okay. I'll just finish that statement. Neutron decayed, right? Okay. All right, let's take a look at the next bit. Um, so this time you're given a graph with how basically you're given the nuclear binding energy graph. Okay,
Mm-hmm.
let's move this down first. Okay. Yeah, I hold on. What did I cut off? Just per nucleon. I'll just write that there. All right, so nucleon. Okay, the questions are uh okay. So here are the questions. So first is outline why high temperatures are needed for fusion to occur. Okay, let's wait for the questions to get pasted here. There. Okay, so again, outline why high temperatures are required for fusion to occur.
Because higher temperatures mean there's more energy being put in,
Mm-hmm.
resulting in fusion. Because like I know, okay, more energy
Uh-huh.
mean it goes closer to the line where it
Mm-hmm.
is fusion.
Yeah. Actually, no. The binding energy curve doesn't tell you how much
I
energy
don't
is
know what else to
needed.
say.
Yeah, but that's a good try, yeah. But let me just note that here. This binding energy curve is not useful for explaining fusion, okay? Or how fusion occurs.
Mm-hmm.
Not useful for how fusion occurs. Fusion or fission for that matter, okay? Okay. But here, the idea here is whenever what happens to nuclei when you put them close together? They will repel, right?
It's yeah.
Okay, so you need enough energy to overcome that repulsion. And how is the high temperatures?
Heat
Yeah, high
or high temperatures.
temperatures mean high kinetic energy for the nuclei, right? When
No, fusion means they come together.
yeah, when Ke is high enough,
They fuse together.
uh-huh, to overcome uh the repulsion of positive charges plus charges, fusion occurs. Okay. So again, the idea here is the kinetic energy is high enough to overcome the repulsion of the positive charges. I'll change that to the word. Okay. And yeah, I'll just write the word here, positive. Okay. All right. Now, the graph, before we answer part two, this graph is useful for explaining why. Okay.
Oh,
This explains why.
is this how a hydrogen bomb is made?
Mm-hmm.
You fuse
You fuse
two
hydrogen.
hydrogen
Yeah, you fuse a
particles.
lot of hydrogen together to form helium. Okay. And how do they
So
achieve
you,
those
but
hyd
sorry,
yeah, how do they achieve
you
the
in,
fusion?
you speed them, like you increase the kinetic energy,
Mm-hmm.
which make it so the charges don't repulse each other, repel each other.
Okay.
No?
Yeah, yeah, it's correct. That's correct. So I'll just write this here before I go. Okay.
Mhm.
Okay. So what you said earlier, yeah, that's correct. So what happens is, again, because of those extremely high energies, they overcome the repulsion and then they fuse, right? So in a bomb, in a fusion bomb, that's what happens. They make they actually have a lot of hydrogen in there, and then it's and then yeah, they kind of get it hot enough for fish fusion to occur. Here's the tricky bit though. How do they actually make it hot enough? It starts with a fission reaction. So there's a fission reaction which heats the hydrogen, and then the hydrogen starts fusing, and therefore kaboom.
Wait, so the hydrogen separates?
No, there's
Oh,
actually
do you mean
hydrogen
from
stored.
like the alpha particle?
No,
Like the alpha decay?
no, not actually. They actually have hydrogen gas stored in the bomb. Okay, but so it's basically got two containers, so to speak. One container contains the fission part to get it all very hot, and then an inner container would contain all the hydrogen. So once the fission happens, it gets very hot. It heats up the literal hydrogen that's already in there.
Mhm.
Okay. And in the process, the fission, of course, the fission means there's a fission explosion, but the hydrogen starting to fuse means there's a fusion explosion. Okay. In a bomb, there's no other practical way to get that get that hydrogen to fuse. No other practical way in a bomb.
Mhm.
But that's what we're trying to figure out in a reactor. Okay. So anyway, going back here, remember that this binding energy curve is not useful for explaining how fusion and fission occurs. It's useful for explaining why they happen in these directions. Okay. So that in fact is the question on the next section here. Outline with reference to the graph why energy is released in both fusion and fission. This one's a bit tricky to say. Okay.
To
But it's
what's
only
it?
one mark, so you just do the overall idea.
Oh, to energy is released
Mm-hmm. Yeah.
to. Okay, each time you go closer to that line, it
Mm-hmm.
changes the element.
Mm-hmm. So what happens to the binding energy per nucleon there?
So for fusion, it increases, but for wait,
For both of them, it increases,
they're
right?
both increase. It increases.
Mm-hmm. So as
Yes.
binding energy increases, binding energy per nucleon, right? So as binding energy per nucleon increases, what happens to
The
the energy released?
it changes the element.
Okay, but remember, we're not asking about the element, we're asking about the energy being released, right?
The energy released.
So as binding energy per nucleon increases, energy is released.
Yeah.
That's the answer. It's only one mark, so that should be the answer.
Oh.
Okay.
Um,
Now, the idea here is before we kind of get confused with that, the idea here is binding energy per nucleon increases, but the total energy decreases. Okay, so an example here would be um, let's use let's use uranium, and then it splits into, let's say, the krypton and argon, right? Okay, so as you know, the Be here per nucleon is gonna be less than the total binding energy of either krypton or argon, right? Per nucleon again. Okay. However, the total Be here, okay, let's give it a value. Let's say that this is 1.1, okay, and then this is 1.2 and 1.2. Let's just say, okay. But remember, this is per nucleon, right? Again, per nucleon. Now, if you look here, though, if you look in the periodic table, or let's just put the atomic masses, let's say that this is uranium 235. Okay. Krypton and argon, let me just look for possible values. Krypton, atomic. Krypton, let's say that krypton here would be uh, 84. And then argon here would be 41. Okay. 41. So so what's gonna happen here? In the uranium side, you're gonna get 1.1 times 235 total Be, right? Binding energy. Here, you're gonna get 1.2 times 84 plus 1.2 times 41 total binding energy in this case. Now, if you do the math, if okay, I'm not gonna do the math here because I don't know if I got the right numbers. But basically, if you do the math though, this left side should still have a total binding energy which is greater than this that for krypton and argon combined. Okay, so this is the idea here. That's why we say that as the binding energy per nucleon increases, the actual total binding energy is less, and therefore energy is released. So we can add that little bit here. Energy is released because total binding energy um after total binding energy decreases. Okay, that's it.
mhm.
All right. Last question for today. So you have uranium 235 is used as your nuclear fuel. And here's another possible scenario: krypton 89 and barium 144. Determine in mega electron volts and using this graph the energy released by this fission, which is exactly what we just talked about, right? So let's take a look now at the actual graph. Where is uranium? Uranium 235 should be somewhere here, right? Okay, so I'll just discuss this bit now. So this is uranium 235. What's that gonna be? That's around 7.5, right?
Yeah, it is.
Okay,
Wait, 7 point. Yes,
around
kind
7
of.
point.
Some.
Okay, so
Yeah,
let's use the estimated value for now.
7.6.
Okay, so for uranium, a Be per nucleon is approximately 7.5 MeV, right? How about the krypton and barium? So barium 144 and krypton is 89. So let's take a look in the graph again. 144 should be somewhere here.
It's around.
Should be somewhere here. This is barium. And then 86, right? Is it? 89. So 89 would be somewhere here. This is your krypton. So for krypton, that's approximately 8.5. And for barium, that's approximately 8.2, right?
Yeah.
Okay, so let's put that in here. So krypton is 8.2 and 8.5. So what's the total BE?
16.7. Oh, you have to add the
You have to multiply these.
7.5.
Okay,
Oh.
not no. You have to multiply this for krypton. 89. Okay. Sorry, it's the other
Oh,
way.
yeah.
This is the 8.5 and this is the 8.2. So 8.5 times
Wait.
89, and then barium would be times 144. And then
I need to remember this, right?
mhm, you need to remember this technique. Yes. So for uranium, you're multiplying this by 235.
So the total. So I add them both at the end.
Mm-hmm.
So I add uranium as well, right?
Yes. So let's do uranium real quick. 7.5 times 235. That's gonna give you 1,762.5.
3,700.
Sorry,
3,700 total.
for krypton and barium, right?
Mhm.
Okay, let's double check that. Okay, 8.5 times 89 plus 144 times 8.2. Actually, no, I got 1,937.3.
That's what I got for without the uranium.
Oh,
Oh,
okay.
we don't add the uranium with
You
it?
don't add
Okay.
here, you subtract. So the
Oh,
energy released would be the difference. So minus 1,762, okay, minus 1,762.5. That's going to give you 174.8 MeV released.
mm.
Okay. Okay. I think we used a wrong value for uranium, or maybe the krypton or the
I think
barium.
it's 7.6
Yeah,
for uranium.
yeah. But either way, if you're really, really careful with how you do it on the graph, it's still the same idea. Okay.
Mm.
All right. How do I know this is wrong? I know this is wrong because this should be smaller.
Is it 150?
Uh-huh.
Okay.
I'm not sure what the exact value is, but let's try to zoom in before we end. Let's go back to the graph, zoom in, see what the actual values are. Okay, so uranium is 235. So 235 should be here. I think this should be here. So slightly large. Yeah. And that would be, yeah, 7.5 is too small. I think we should have used like 7.6 or 7.8.
Mhm.
7.6 would have been better. All right, for barium, let's take a look. 144. 144 is right here on this line. We should have used 8.2 for barium. And then for krypton, okay, let's take a look. Krypton was 89. So close to 90. So should be here. Krypton should be closer to 8.6. Yeah. So anyway, same idea. You just change the numbers and done. If we change the numbers, this should be around 7.6. I'll use gray. So 7.6. This is still 8.4. sorry, not 8.4. That's going to be 8.6 here. This is going to be also 8.2. So 8.2 still okay. But either way, same idea. Doesn't really matter how you do it, as long as you do it this way, or what numbers you use, as long as you do it this way. Okay. Is this
Mhm.
is that the last question? Yeah, that's the last question
But
for
this
now.
this is the energy released equation. You
Hmm.
multiply binding energy by atomic
By
mass.
the mass, yes, correct. By the mass.
Yeah. Okay.
Okay, so total
Mass.
BE is the mass times the BE energy in the curve.
Wait,
Okay,
we're finding total BE
yeah,
by multiplying BE
per nucleon,
by.
right? So the idea here is
Oh,
because
okay.
the
Binding
curve, I'll
energy.
just like to say it this way: the curve gives BE per nucleon. Okay,
Mhm.
binding energy per nucleon. So to find the total binding energy, so total BE should be equal to um, BE per nucleon times number of nucleons. And this is the same as saying atomic mass, which is identical to atomic mass.
Mhm.
Okay, so I'll just rewrite it here. This is going to be BE per nucleon times atomic mass. Done. Okay.
Yes.
All right. Then to find the energy released, you find the difference in the total BEs before and after the reaction. Okay. I guess we can end it here for now, CJ, because it's getting a bit late, I guess. All right. So we'll continue
Mhm.
your exams on Thursday. I think we'll have a meeting on Wednesday, if I'm not mistaken. Let me check the
Okay.
calendar. Let me check the calendar first. Okay, so okay, today's the
Maybe Tuesday.
21st. Yeah, Tuesday's fine.
I think I have a meeting on Thursday.
Ah,
Well, I
right.
put
We have a meeting on
a meeting on
Thursday.
Thursday.
We have a meeting on Thursday, but that's for pay. Yeah, and then I still see that we have a paid meeting for Sunday. You want to move those?
Reschedule.
Yeah.
Mhm.
All right. Yeah, go ahead. I think you can reschedule that yourself because we still have time, right?
Mhm.
Right.
Yes.
Let me see where else you have a paid session. I think that's it. That Sunday's our last paid session. The rest are just reserved for now.
Oh, there's also one.
On
Okay. Okay. Yeah.
Thursday, can you double check next Thursday on the 2nd of May?
Yeah. I can reschedule that
All right.
to.
Okay. And then on the 5th, that's already reserved. So that means it's not a paid session anymore. So you don't have to worry about Sunday. Just
Mhm.
worry until the 2nd of May. Okay.
Mhm.
All right. So okay.
Okay.
All right. So we'll end here tonight, and I'll see you again on Tuesday.
Okay.
All right.
Thank you.
See. All right. Bye bye, CJ. Have a good evening. Bye bye now.
Bye bye. You too. Bye bye.
Okay. Where is that? Okay. So that's the end of the stream. So thank you again for those who are in. Okay. Oh, I did get something on Facebook. It looks like in French. It's in French. I'm going to get that. Uh, I'll see what this is first. I'll get this translated. But anyway, okay. Let me just do a quick translate here. Haitian Creole. Okay, which is based on French. Okay, I'm going to ignore that. That seems a bit like spam, so I'll just ignore that for now. So anyway, um, that's it for the stream. So thank you all for if you're listening, thank you. And here we go. We have Okay. Anyway, for Instagram, I think we finished the stream after an hour. We were doing it 2 hours today. So, that's something new for me. All right. So, something learned. I think I'll just redo it next time. Okay. So for now, that's the end of our session. So remember, don't remember to if you're new to the channel, please subscribe, like, and share all the videos. We stream live on Facebook, YouTube, and Twitch, and on Freaky Physics at Freaky Physics. And then for Instagram and TikTok, we do share certain things there, mostly shorts. So if you find that interesting, follow this as well. So that's it for tonight. Again, thank you for CJ earlier, and thank you all for whoever's going to watch this. And with that, I bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world, and stay freaky, everyone. Bye bye now.